Heat pipe OTEC, climate mitigating energy production. Global warming is the accumulation and storage of trapped solar energy. By far, most of the heat of warming is going into the oceans. Over the last 30 years, this heat has gone deeper and deeper into the ocean. To mitigate this phenomenon, first greenhouse emissions must be halted. Then the trapped heat should be reduced by conversion to productive energy. The latest finding by scientists at the National Center for Atmospheric Research is since 1960, the oceans may be storing 13% more heat than had been previously estimated. The top 75 meters of the oceans have warmed in an average 1/100th of a degree Celsius per year since 1971, whereas between 500 to 2,000 meters, oceans are warming by about 2/1000ths of a degree a year. Ultimately, the ocean heat will have to come out as the atmosphere and ocean come into equilibrium. The longer this equilibration takes, the better, considering excess heat in the atmosphere is transported rapidly to the poles, where it melts ice and increases sea level rise. OTEC is a method of converting surface ocean heat into productive energy. Global warming is a manifestation of the OTEC resource becoming too efficient, because temperature gains due to climate change are larger at the sea surface, which heats faster than the ocean as a whole. The prime energy producing OTEC regions in this graphic, shaded from red to yellow, show where the surface is at least 24 degrees Celsius higher than the universal 4 degrees Celsius temperature of the ocean at a depth of 1,000 meters. Heat moves from the equator towards the poles. From between 2 and 5 petawatts of heat is moved naturally this way annually. Most of this movement is through the atmosphere, but about 10% is through the oceans. Due to global warming, about 335 terawatts of this heat is being left behind every year. Although this heat is moving into deeper water, we are not deriving the benefit of this natural thermal stratification. Conventional OTEC plants will move surface heat only to a depth of about 100 meters, where it mixes with colder water from deeper sources. It is essentially a dilution solution to global warming. This heat returns to the surface by diffusion at a rate of 4 meters a year. Therefore, it is back at the surface in as little as 25 years. As indicated in the following graphic, it would be beneficial in terms of sea level rise, were we able to move the heat accumulating at the surface to deeper water where the coefficient of expansion is less, and where the heat is unavailable to storms and where it cannot melt polar ice. To stop global warming in its tracks, we need to turn off surface heating elements and turn on new ones at a depth of 1,000 meters. These elements would burn for between 3,300 and 6,250 years and produce between 13.5 and 25 terawatts of power annually prior to burning out. In this way, the heat of global warming can be reduced, reused, and recycled until it's completely consumed. Heat pipe OTEC is a method of stopping the accumulation of surface heat and moving it instead to deep water. Due to the smaller size of the piping for these plants, compared to the cold water pipes of conventional OTEC, they can be built for less and can produce higher capacities. The oceans are the world's largest solar energy collector. Every day, 60 million square kilometers of tropical seas absorbs 1 quadrillion megajoules of solar energy, the equivalent of 170 billion barrels of oil. It is estimated that 100,000 of these plants of 250 megawatt capacity would produce 25 terawatts of energy annually. In order to process or move heat, you first have to collect it. My colleague, Dominic Michaelis, developed the energy island concept for extracting energy from a given area of the tropical ocean. These floating structures amalgamate various renewable energy systems, including wind, wave, sea current, solar, and OTEC, to maximize the potential of the tropical surface. In accordance with the following graphic, about 23.5% more energy can be produced from this combination compared to OTEC alone. To collect solar energy, this triangular island of equal sides of 735 meters uses solar panels. The wave energy is converted to hydraulic energy with a system similar to the Sea Razor pump system. Wind energy is collected by vertical windmills. There is also the potential to produce energy from evaporation. The bulk of the energy of the system, however, is derived from OTEC, which is initiated by the indirection of surface heat below the island into a series of evaporators. To ensure a constant flow of warm water through the evaporator, the system is driven by a pair of thrusters, and another at the front of the island that also provides directional impetus. The constant surface ocean current is between 1 and 2 meters per second. The thrusters move surface water through the evaporators at twice this rate. The mass of the surface assembly is comparable to the largest ocean liner, the Harmony of the Sea, which has a gross tonnage of 257,000 net tons. This vessel cruises at 22 knots and is powered by 3 20-megawatt thrusters. The heat pipe OTEC system requires about 11 megawatts of power to produce the required movement of water through the evaporator. This is less than 1/4 of the power generated by the island system, absent the inclusion of 200 megawatts of OTEC power. Hydrogen, mechanical, and electrical energy is stored in surface units, which can move the system even when OTEC is not operating. The evaporator consists of a shell, an array of 10 centimeter by 34 meter long pipes arranged in a circular pattern of 13 meters diameter through which seawater flows, and a fluid inlet and working fluid. Surface water heats the working fluid to produce a vapor. The vapor escapes through a collector. The vapor flows to a chamber within a ball joint, which can swivel through a range of 45 degrees to accommodate a range of movement of the lower assembly to and from deep water. The ball joint consists of an inner layer in which the vapor flows, a second layer in which a condensed working fluid is returned back to the surface, and a third layer in which hydrogen and oxygen are brought to the surface after they are produced in an electrolyzer. The ball joint is encased in a block which is attached by cables to a similar block at the condenser end of the system. The vapor flows down an internal pipe to the maximum depth of 1,000 meters. The heat pipe is the essence of the heat pipe OTEC system. It is a heat transfer device that uses the phase changes of a low boiling point working fluid to conduct heat from a hot surface, such as the tropical ocean, to a cooler reservoir, such as the ocean at a depth of 1,000 meters, where the temperature is virtually universally at 4 degrees Celsius. The thermal conductivity of such a device can be as much as 200 times more than a metal conductor like copper. The typical heat pipe is a sealed tube into which a working fluid has been inserted. Heat is applied to one end of the tube, causing the fluid to vaporize, creating pressure. The pressurized vapor flows to the cool end of the pipe, where it condenses by releasing the latent heat of condensation of the vapor into a cold reservoir. The condensation of the vapor creates a partial vacuum, and the pressure differential between the ends of the pipe allows for the rapid transfer of the heat from the evaporating to the condensing end of the pipe. A wick structure then conveys the condensed fluid back to the top of the pipe by capillary pumping to repeat the cycle. With the heat pipe OTEC system, instead of a conventional wick, the working fluid is returned to the surface by capillary pumping in aluminum sponge along the path of a helix, which functions like a stationary Archimedes screw. The following is a cross-section of the pipe, which consists of the outer pipe, the helix, the aluminum sponge in which the returning fluid moves, and the inner section in which the gas descends. Such a device goes a long way towards overcoming the parasitic losses of the conventional system. The helix and aluminum sponge also support and counteract the tremendous pressures operating on a pipe containing vapor, operating at a depth of 1,000 meters. This concept would have to be tested and verified over an extended period, and inspection, maintenance, and repair constraints established before it could be scaled but its benefits would be worth the effort even if the approach didn't pan out. In the alternative, pumping 2,750 kilograms per second of anhydrous ammonia with the heat pump system is more effective than pumping 142,300 kilograms per second of cold water with a conventional approach for every megawatt of power produced. An alternative arrangement would be to use carbon dioxide as a working fluid in view of the closeness of the density of the gas and the liquid phases as carbon dioxide approaches the critical point, which is 31.1 degrees Celsius. Although OTEC's surface temperature is typically about 28 degrees, the temperature at the bottom of a 1,000-meter-long column of a gas increases close to the critical point at which the gas functions more like a liquid. This is advantageous for the turbine. Gravitational potential is also conserved in such a system due to the proximity of the mass of the gas and the liquid near the critical point. Also, a significant accidental release of carbon dioxide would be less biologically impactful than a similar release of anhydrous ammonia, since the concentrations in terms of immediate danger to life and health are 40,000 parts per million for carbon dioxide against 300 parts per million for ammonia. Reaching the operational depth of the system, the vapor then enters a turbine housing, where it is directed by stators against the vanes of the turbine to produce mechanical energy. The spent vapor enters the condenser, which is essentially the evaporator in reverse. The vapor is condensed back to fluid as it flows over the condensing tubes, which contain the 4-degree water flowing through the pipes. The impetus for the flow of water through the pipes is provided by the surface thrusters, since the condensers are simply being dragged behind. The condensers are of equal size and quantity to the evaporators. Piping collects the condensed fluid, which enters the bottom block and through the second layer of the ball joint and then into the outer pipe, where the helix and capillary pumping return the fluid back to the surface, where it re-enters an evaporator to complete the power cycle. The shaft of the turbine is connected to an electrical generator consisting of a series of rotors and stators which convert the rotating energy of the turbine into electrical energy. OTEC's greatest energy potential is far offshore. Thus, the conversion of the produced electricity to a chemical energy carrier such as hydrogen or derivatives is required. This requires electrolysis, which directs electrical energy into a series of cathodes and anodes, which split water molecules into the constituent parts, hydrogen and oxygen. With the system described, a series of graphene-based sieves remove salt from the seawater to produce pure water. This is accomplished by reverse osmosis, as the semi-permeable graphene membranes remove ions, molecules, and larger particles from the seawater. The ambient pressure of the water is 100 bar, whereas pressure of only between 40 and 82 bar are required in the conventional reverse osmosis process. By electrolyzing pure water, chlorine is not as problematic as is the case with normal electrolysis of seawater. The byproducts of electrolysis with this system are solely hydrogen and oxygen. Hydrogen is costly to pump due to the high pressure required by producing hydrogen at these pressures. The gas returns to the surface 72% of the way toward the 700 bar required for transportation applications. The relationship between depth and pressure is logarithmic. The hydrogen is collected in tubes within the electrolyzers and is conveyed back to the surface, where it is collected in tanks, which can be offloaded to transportation ships. The oxygen collected by the electrolyzer is directed to the surface into vents, and from there it is sucked into tubes of the evaporator. Biofouling of surface infrastructure is a problem remedied by ozonation. This oxygen also helps address the escalating problem of ocean dead zones. Also, the warming of the oceans is leading to smaller fish yields due to the declining oxygenation of the water. In the alternative, negative emissions OTEC is a proven electrochemical process of generating hydrogen that also consumes carbon dioxide. Converts the carbon to a common form of ocean alkalinity that provides high-capacity carbon storage, while also helping counter the chemical and biological effects of ocean acidification. For each gigawatt of continuous electrical power generated by this process, Roughly 13 gigawatts of surface ocean heat would be directly removed while producing 130,000 tons of hydrogen annually, avoiding 1.1 million tons of CO2 emissions a year and consuming and storing as dissolved mineral bicarbonate approximately 5 million tons of CO2 a year. This carbon dioxide mitigation would result in an indirect planetary cooling effect of about 2.5 gigawatts. Such negative emissions energy reduction and global warming mitigation would avoid the biophysical and land use limitations posed by methods rely on terrestrial biology. The base minerals and salt electrolyte required for this electrochemical conversion are globally abundant. Therefore, the scale of the process might only be limited by the cost and availability of the non-fossil derived electricity produced by the OTEC. The subsurface component of this system requires ballast, which is consumed by the production of hydrogen and thus has to be replenished in any case. Ships like the one shown here service this need. To keep the deep water section of the system at the operational depth of 1,000 meters, an adjustable dive plane and ballast shifting are employed. These also facilitate the ready return of this equipment to the surface if servicing is required. In this regard, the simplified mechanics of the system and passive fluid movement through the condensers and electrolyzers limit this requirement. Climate forcing is quantified at the tropopause in watts per square meter. It is the difference between the sunlight reaching the planet and the energy it radiates back to space. Since 1975, the Earth has warmed at a rate of 0.15 to 0.2 degrees Celsius per decade. Since the surface area of the Earth is 510 million square kilometers, this warming amounts to about 2.5 watts per square meter. By comparison, each major tropical storm releases between 50 to 200 terawatts of heat. Again, we are reminded the oceans are accumulating about 335 terawatts of heat annually. According to NASA, Hurricane Katrina cooled water temperature of the Gulf of Mexico by more than 4 degrees Celsius in places along its path and cooled the entire Gulf by about 1 degree. 1 or 2 good hurricanes, therefore, should theoretically be able to sequester all the heat the oceans are accumulating due to global warming. Studies suggest, however, only about a quarter of the heat mixed downward by tropical storms makes it into the permanent thermocline below about 200 meters. 3/4 of the heat is reabsorbed by the mixed layer, and in the winter and spring months it is transported out of the tropics toward the poles and back into space. The objective of heat pipe OTEC, therefore, is to remove surface tropical heat well below the 10 to 20 meter deep mixed layer of the ocean and well into the thermocline. The deeper the heat is moved, the better, considering its return rate is on the order of 4 meters a year. With heat pipe OTEC, the descend rate is about 70 meters per second. Surface temperatures rebound quickly after a major storm, and back on the surface the heat mixed to only a few meters can be a positive feedback that strengthens subsequent storms that traverse the same segment of the ocean as it happened this summer in the Atlantic. For this reason, heat pipe OTEC is more environmentally beneficial than conventional OTEC. Like a tropical storm, it cools the surface of the ocean and keeps the heat down for at least 250 years. Where hurricanes provide a gross and essentially temporary warming effect, heat pipe OTEC supplies a cumulative, semi-permanent cooling of the planet. They cool the surface locally to cool the planet globally. These plants can be localized magnets for the heat of warming, which in turn keeps the heat away from the poles. In fact, 1,000 meters deep in the vicinity of the equator is as remote from the poles and the major consequences of climate change as you could get on this planet. Heat rises, but before it can get back into the atmosphere, which is the shortest route back to the poles, the heat can be driven back into the depths through the production of more energy. In this way, the rate at which the overall heat content of the oceans and the atmosphere equilibrate can be governed. The logical question then is, how much productive energy can be derived from 335 terawatts of accumulating heat, bearing in mind the pace of warming is increasing and is not likely to be reined in the immediate future. Working from a surface temperature range of 28 degrees Celsius and 4 degrees in the deep, the theoretical Carnot efficiency is 8%. Practically, efficiency of conventional OTEC is closer to 3%, but a study by Melvin Pruitt, Los Alamos Labs, suggested a heat pipe OTEC design can have an efficiency as high as 7.6%. The main reason for this improvement is the fact a column of gas 1,000 meters long increases in temperature by about 5 degrees due to the pressure being exerted on it by the gas above and the decreased water movement of both warm and cold water, less ecological damage and smaller pipe diameters and less need for fluid pumping. Somewhere between 3.4 and 25.5 terawatts of renewable energy therefore can be produced by these systems, which equates to about the same to 1.8 times the amount of energy being derived from fossil fuels every year. Since these systems convert only between 4 to 7.6% of the heat of global warming a year, between 96 to 92.4% is sent to the deep. Once the residual heat returns to the surface, it becomes a new input for another round of energy production, and as a result it takes from 3,350 to 6,250 years to completely reprocess the heat of warming. No other energy system provides this perpetuating economic and environmental benefit. The scientific literature suggests that OTEC would initially cool the surface layer of the ocean in tropical regions with a compensating warming trend elsewhere. With 240,000 plants, nominally rated at 100 megawatts, deployed across the entire OTEC region of 114 by 106 square kilometers, essentially each plant centered within an area of 22 square kilometers, producing a net 14 terawatts, would cool down the OTEC region, but that region would then be able to absorb more heat from the outside, such that the cooling effect would be less. The experience with tropical storms, however, suggests that this is not the case. After storms, the surface temperature rapidly rebounds, but the reason is because the bulk of the heat has not been driven far below the surface and thus rapidly returns. Sent to 1,000 meters with a heat pipe, it would take centuries for this heat to return, and even if other heat from outside the area replaces the sequestered heat, the net effect is still a small but beneficial cooling of the ocean surface. A single OTEC plant operating within a 22-kilometer square patch cannot stop any particular storm, but the heat that has been building up over decades, to the point where the strength of these storms is increasing, can be reduced over the long run. The literature suggests that the cooling of the OTEC region would be offset by warming elsewhere, such as the immensely productive upwelling region of Peru, which would not be acceptable. The point is, though, conventional OTEC is an upwelling strategy in the first place. This graphic shows the relationship between net OTEC power production and upwelling intensity of cold water, WCW. As this graphic shows, the yearly average global OTEC power rating rapidly decreases as a function of the upwelling intensity. Beyond an upwelling of 5 meters a year, OTEC production declines dramatically. With heat pipe OTEC, on the other hand, the upwelling rate remains constant, regardless of the production. This is because the surface water remains in place, as does the deep water. It is only the heat that moves rapidly downward and slowly upwards through diffusion. The heat is then recycled to ensure slow attainment of a new steady state between the ocean and atmosphere, and with minimal impact on the thermohaline circulation. The 1,000-year average temperature change of the surface at 55 meters is shown in this graphic, when the cold water upwelling rate is 20 meters a year, which equates to an annual power level of about 30 terawatts. The OTEC region is within the black lines, and the 1,000-year yearly average temperature change in a deep seawater intake layer centered at a depth of 1,160 meters is shown in this graphic for the same upwelling intensity. First 55 meters is roughly the depth at which waste heat from both the evaporator and condenser of a conventional plant is discharged. At an upwelling rate of 20 meters a year, it would therefore only take 3 years for the heat moved by the conventional plant to return to the surface. The long-run surface cooling effect is therefore negligible. Even at an upwelling rate of 5 meters a year, which equates to a power level of 7 terawatts, it would take only 11 years for the heat moved to resurface. In 1,000 years, this heat would then be recycled 91 times. With a heat pipe, on the other hand, it would take 250 years for the heat removed from the surface to resurface. The top graph shows that in 1,000 years the surface is cooled by about 3 degrees in the tropics and is warmed by other regions like the North Pacific and the Atlantic and off the southern part of South America. Since we are cooling the surface of the ocean currently at a rate of 1/100th of a degree a year, by moving this heat to 1,000 meters and then recycling it 4 times after it gets back to the surface, the most the surface could be cooled and the other parts of the ocean warmed would be only 4/100th of a degree. The same thing applies for the warming of deep waters with heat pipe OTEC. The most the warming impact would be 4/100th of a degree. The only way you get the results shown in the previous figures is to essentially overturn the entire ocean between a depth of 1,160 and 55 meters 55 times. With the heat pipe, the maximum overturning would be only 4 times, and as a consequence you would have to produce 96 terawatts of power to replicate the same effect. As a consequence, 25 terawatts of power is doable with heat pipe OTEC, particularly when you consider this would be just keeping up with the heat currently being added annually to the system. The literature suggests large OTEC scenarios implemented stepwise have essentially no chance to take place except in numerical experiments. It is suggested here that this is because the modelers have taken the wrong approach to the problem, and as a consequence, the climate aspirations of mankind are being shortchanged. Instead of less than 100 years of OTEC production at full capacity, depending on the efficiency of the systems, we should be looking forward to between 3 to 6 millennia of climate mitigating energy production. The bottom line is, with heat pipe OTEC, the surface should be cooled by 4/100th of a degree as the deep is warmed by the same amount, and the difference would be distributed throughout the entire water column and throughout the entire ocean as is the accumulated heat of global warming. OTEC efficiency would not be impacted because the delta T between the surface and the deep will remain the same. In the alternative are the IPC scenarios of as much as 4 degrees Celsius by the end of this century. So the only remaining question is, what will all this cost? The following schedule shows that beyond the initial startup and engineering costs of about $10 billion, or about 3% of the damage caused by hurricanes Franklin, Harvey, Irma, Katia, Jose, and Maria in one season, these systems start replacing and outcompeting fossil fuels in as little as 10 years. Surface heating is the primary consequence of global warming. We entrust heat pipes with the thermal integrity of our computers and expensive electronic equipment. Why would we do less for the planet? The devastation of Japan by Fukushima and of Puerto Rico and the Caribbean by this summer's hurricanes point the need for an energy infrastructure based on hydrogen for islands, which in turn should become a universal standard. Artificial intelligence is seen as a killer of jobs, but a little old-fashioned anthropogenic intelligence can instead turn the global warming problem into a planetary panacea. Stephen Salter, Bill Gates, and others have patented the idea of using thousands of tires lashed together to support giant plastic tubes, which extend 100 meters deep into the ocean to force ocean surface water down to the deeper ocean, where the warm water would mix with cooler water to reduce the potential of hurricanes. Heat pipe OTEC provides the same benefit along with trillions of watts of renewable energy.